now and what's the scope of it and different other stuffs. So yeah, without waiting, let's just start. I'm just trying to share my screen, and I guess Balaji is recording it. Okay. Yeah, and also during the time I will be shared, just please feel free to actually like ask any sort of question. But yeah, if you have any sort of like question which is like potentially be taking time to discuss, then please just leave it in the chat. If we find the time, then we can actually discuss here. Otherwise, I will be like going to the channel and I will be try to like discuss all the questions. So here we are, and the flow of this like meeting will be going something like this. Like I'm having some slides here that I will be like sharing after this meet, and at the same time, I will be also be like writing in the whiteboard if required to explain. And yeah, that's how the things we are thinking to go. So yeah, so graph machine learning, it's actually one of the hottest topics other than transformers actually after transformers. So the thing is like the machine learning that we are specifically actually that is implementing on the graph data structures is what we can say is like graph ML. But the very first question comes like we have transformers, right? We have CNN types of architectures, we have sequential architectures like listing GNN and GRU, etc. Then why we are trying to use graph ML in the first case? Then actually the answer comes like before going to deeply understand why we want to use graph ML, we can actually get some perspective by seeing some sort of some real world example. So we can actually see from different sort of products that in the real world that is actually dominating the real world market. And one of the products that we actually use in each and our everyday life, even I also use it, especially the Uber Eats and the Google Maps actually, and even the Pinterest. So this is so I will be like taking a deep dive of how they are like using the graph image here, but in a very intuitive manner. So can you even just like give me a thing that am I fully audible, right? And I sometimes face some sort of network issue, but yeah,
We can hear you perfectly, Anindya.
yeah,
Ask me.
great. So let's just come with the thing in the notion of why we are using the graph element. So one of the thing is like if you have actually suppose we have like this country, we can actually think our country. Okay, just pardon my drawing, but suppose we have this country here, and each and every countries are actually having some sort of roads, right? We have this roads here and there which are actually connecting from one place to different places. Suppose take a segment of this road, and we have suppose I'm having suppose this destination A to destination B and I am having some sort of roads here and there. Now, what you can actually visualize this thing as some sort of a graph data structure. How we can actually visualize it is like you can see you can treat or you can actually take each of the segments of the nodes as some sort of the nodes which are actually connected through the edges, and you can think of this some sort of the graph, and you can actually do a lot of tasks from this. One of the like tasks is like you start from one node and it will be like going to a destination node, and you can actually find like based on the current traffic you're having through the satellite things that we are actually the researchers are actually using. We can actually use those sort of informations to actually get the amount of time that will be like taking from reaching from part A to part B. So that is actually been done and been deployed, and you can actually find the paper. So yeah, one thing to actually mention here, all the things that I have actually linked here, the corresponding resources you can actually find in the notes section. And if I forget to text like provide some of the notes, then I will be like updating those later. But yeah, once I share the slides, you can actually go to some take a deeper dive if you are more interested, right? So yeah, that's how Google Maps nowadays like work on predicting the estimated time of arrival, and this has been like recently deployed. And not only this, GraphML has a like a huge amount of like contribution when it comes to recommendation engine. So suppose you are like suppose in the Pinterest you have this concept of pins, right? Like you start from one pin. Suppose this is my pin one, then there can be, suppose you are actually taking up, you're seeing a pin of suppose a Pikachu, a Pokemon, and after that, like Pinterest will actually try to not only give you the other pics of Pikachu, but also which has like a very close like recommendation, or it has some very close similarity with the what sort of pictures of Pikachu are you actually seeing, right? So so the thing is, like, you go from one pin to another pin and you actually get some sort of like recommendation from, like, this is suppose the recommendations of different other pins right there. So all of this can be actually visualized as some sort of a graph problem. And how you can actually visualize it actually is, you can actually, let's just like not only think about a pin, but you can actually think suppose like suppose a social network, like how Facebook actually does is, Facebook has a very big database of like the people who are actually using, right, of the users. So you can think yourself as some sort of node here, and you have some sort of like features like your age, your gender, etc., etc. And you're actually connected with, suppose you are people A, and you're connected with different other folks, right? So all of these are your friends, and B has some sort of friends like suppose E and F. B has some sort of friends like G and H, and this actually goes on with a huge, humongous graph. But based on this, how graph ML you can apply is like, based on the trends that you have, you might have some sort of probability that you, the person A and person E, might actually share some common interests, some common backgrounds of interest. So the app or the potential recommendation engine will actually like try to recommend these people as becoming their own new friend, or like recommending the people to actually put on the friend request or stuff. So yeah, the recent graphical like research has a lot of like, is putting a lot of effort in order to like fine tuning these the recommendation engines, not only the social networks, but you can also like see, so the recommendations can be like classified into different sort of other classifications based on the type they are, like the type of recommendation they are actually using. You can do it on the social networks. You can actually do on the user item graphs or user item networks, different sort of networks. One example of the user item networks is like, suppose you are taking some sort of products from Amazon. So suppose you are the users here. Suppose I'm this user, user one. Here's this user two. Here's this user three, and till it's actually going to user n. And suppose I have some list of products. Let us assume that these are some list of suppose foods you're trying to take. So suppose I'm having some choice of foods from here and there. User three has some sort of like choice from these, like this is suppose food one, food two, food three, and stuff like suppose food k. And similarly, like user n has some sort of like recommendations of some foods. Now based on this, based on how frequently you're buying a food, how much different diversity of the food you're taking, based on all this information, there will be a black box kind of thing which is actually operating on the graph, that will take all this information, and then finally it will process it, and it will take you to find, actually give you the newer recommendation. Like you might have some preference to try suppose some of the new foods, suppose like this food, like anyways suppose you're trying Chinese food and you like some Indian food, there might be a preference that you might like an Indo Chinese food also, right? So yeah, so this is how actually recommendations also works. Other than that, it's not only about the things that you actually see in the daily life, but in the academic research also, it's been a huge, huge progress once like graph has been landed. And one like a very good example is actually in the simulation. So the simulation is also something like really great thing. I mean, we have actually read in our, like when we will in our schools, we have actually read like H2O, or the what I mean a water as an element, natural element, can be like described as some sort of like some combinations or some chain of like molecules, right? So now the thing is, like each and every element has some sort of like a defined structure. And suppose water has some sort of like the water actually has some sort, we can like simulate the flow of the elements. It might not be water, but it can be any of the liquids or gases. And the flow of the elements can be actually, we can actually visualize the flow of the elements from a different perspective by taking it to a molecular level, like how the molecules actually move from one place to another places. And so you can actually think those sort of molecules, like suppose this is my one of the H2 molecule. So you can actually think those as some sort of a node. And suppose the that is the bond between each and every like molecules, you can think about this some sort of edges. And now with respect to time, what you're trying to do is like you're trying to predict how this molecule, suppose this is my molecule A and this is my molecule B, how this molecule is actually accelerating, how B is like decelerating or accelerating. So you're trying to find the relative acceleration or velocity, etc., in order to. So suppose you are finding the accelerations or the velocity which you're trying to target to predict. You find for one or for one molecule. So if you then try to predict for suppose n number molecules, it will try to give you a potential kind of a simulation in the long run. And that's how people, researchers are actually been successful to find like come up with like very accurate sort of like this simulations. And there are actually reasons why graphing is actually getting so much popular, and like researchers are actually being so much successful, suppose in the simulation stuff, or mainly in the type of data structures which can be actually represented on the graph. So there are like several reasons which I'm just coming back to the next slides. Anyways, it's not only in the physics or in the academic in the academic cases, but also why we cannot miss the healthcare, right? So there is in the domain of polypharmacy, it's actually like really very much interesting. I mean till now, I guess you guys can actually guess it. Like we can literally can we can actually like we can literally represent in each of the anything, like anything which we can actually see in our like daily spaces. We can actually think them, suppose some sort of like a graphs, some sort of a graph data structure. We might not like give a guarantee to the feasibility, but still, I mean, we can visualize it, right? We can actually so one of the like that we can be seen in the healthcare also. I have like described about these molecules in biological world also. You can actually think like suppose I have this, suppose I let's give a real world example. We have seen all this like this is one of the most famous like molecule, right? I mean, I have actually read all the stuff in chemistry and it's in class 10, 12. But the thing is like you can actually visualize this like the symbols in some sort of a graph. How you can do that is like you can actually think like carbon is a molecule and it's actually attached with some hydrogen molecules, something like this. And this hydrogen molecules, you can carbon, hydrogen, and other stuff. You can actually think this some sort of like the nodes of the graph, and these things as the bonds between each of them as some sort of the edges of the graph. So what I'm trying to tell you guys till now from all these slides is to trying to help to visualize how to take a raw problem and you're translating that problem to a graph problem. I mean, that's the very important thing first. We have to actually understand, or we have to actually translate one like a very raw sort of a problem to a graph problem. And once we can like figure out that perspective, then we can actually use that graph and apply some like some ML algorithms, some real algorithms in order to get some task done. So this is the very first step. And so the thing is like, so here is like you can how you can visualize a chemical as a graph. And so one thing, so one like a real world perspective which can be done is like all of this like structures can be like some sort of a graph. Then similarly, using this, so the thing is like you can actually if this simple sort of like molecules can be visualized as a graph, then you can actually think some complex molecules like the complex drugs which are actually been helpful for the human mankind can also be thought of. But I don't know how much you guys know about it, but actually creating a new drug which can be potentially be very much useful for the humankind takes a huge amount of time and a huge amount of like economy amount is actually spent in order to make a new molecular drug. So molecular drug discovery is like a very huge domain where graph machine learning is trying to like capture, and it's doing really great. And it's been like the whole process. Suppose the whole process is supposed taking more than 10 years. You can actually cut that down into some months now, literally. So that's how the graphical thing is now is actually accelerating with the help of this graphical and like the different like the generative modeling. What you can actually do is like you can now use those stuff and you can actually predict and you can like come up with like new molecular structures new like molecular drug structures, which is like potentially and has been like useful for come up with like new drugs which are like really very much helpful for the mankind. And the example which I have like have shown this here is actually like suppose you are taking suppose you have some sort of disease and doctor has prescribed you to actually take some sort of medicines and some sort of antibiotics, and at the same time suppose you have some sort of cholesterol or pressure, diabetes, etc. So you're taking some sort of other medicines beforehand. So you can actually think of those like what all these medicines are actually doing in the biological level. They are actually like there are some sort of chemical which are actually some of them are actually binding with the proteins and other stuff in order to do some biological thing. But the thing is like you can actually map all those like the interaction between one drug through the protein. So suppose you have this protein P, and this protein has some binding site, and suppose you have this drug D, and this drug actually binds with this protein P. Similarly, the thing is like suppose you have some another drug which might have some sort of like a correlation or some dependency with some protein, this protein P or another drug D. So suppose this is my D1 and this is D2. So the thing is like so using that you can also like suppose you can actually map out this different sort of interactions between these proteins and drug, and from that you can actually come up with different sort of some sort of like side effects, like any kind of side effects that can be actually being seen by taking like suppose multiple type of medicines which you are taking at the same time. And the potential patient might be like stopped from being taking the medicines which should not have been taken for this sort of like ill interactions that can be analyzed here. Coming back to these slides, so that's a huge contribution that GraphML does in the healthcare. And another is the like a very the like very hot topic right now is the geometric deep learning, where you can literally you can actually, I mean, represent any of the thing. I mean, literally any kind of a real world problem or any kind of a natural interaction as a graphical problem. So I wouldn't try to go to more into depth into this, because the thing is that I'm also a very like I'm just trying to learn all the geometric deep learning stuff. But anything, I mean, suppose in the computer vision you have seen the human mesh like structures, right? And even like you have also heard about the point cloud structures. And there are like in the mathematical domain also there is this like terms which is like geometric spaces known as the manifolds, and the other like complex geometric spaces like these stuffs are there. So we can actually do a lot of stuff. For example, one of the things we can examples what I can actually show you here is the human mesh like structures. So here is like the human mesh like thing structures. You can, if you just like observe it carefully, then you can actually think this all of this some set of like a nodes and edges, because the mesh has some sort of like fundamentally, if you just go through the fundamental level, then what you can actually say is like all of those is made of some sort of like small dots connecting with each other. You can think some those dots to some sort of nodes, and each dot has some. Suppose you can actually think about. You can actually let's just like break it down to a very simple problem. You have heard about pose estimation, right? Like in the pose estimation, you can literally draw the pose. Again, like ignore my drawing, but the thing is, you can actually think of this like this is a human pose, and if you see this into a two-dimensional domain, then you know that each of these dots has some sort of x and y coordinates. And literally using some sort of like techniques, I do not want to go to the techniques right now because it will make things complicated. But think of that you have some sort of like a black box, which actually suppose for some sort of like time t, I'm holding in this position, and the time equal to next t seconds, I will be bringing like suppose my position will be changing. So this like this black box can actually predict that what position will be during the next timestamp. So, and you can actually see the change of the position can be actually be calibrated to this thing, like the relative change of the position of each node. So suppose this node has been changed to suppose here like the x1, suppose this is suppose 5 comma 2 is my initial position. The next position might be 6 comma 3, I guess. So what this like the graph ML or the GNN, the graph neural network does is like this is one of the structure. there could be like different other like tasks that you can actually do with all this stuff. But one like very interesting stuff is like you can actually predict the nodes, like where the nodes are actually going, and eventually you can like simulate it, and you can actually predict the next action or the next movement of what the potential subject can do. So all of this actually come up. So all of the like the when you are like dealing with like the natural occurring that is problems which has some geometrical significance, and you can like when you're also like correlating the stuff as a graph, you're just think you're changing your perspective, and you're thinking all those stuff as a nodes and combination of nodes and edges. You can actually then this like this whole topic or this whole thing actually comes under the geometric deep learning. There are like a lot of stuffs here. Each and everything that I've actually told is a research paper, or is a topic, or we can actually discuss each and every topic like in a new session on. So we cannot go to a very into a depth here, because it's just all you have to understand is like two things here. Like we can use a lot of we can use graph ML in a lot of ways, and also the thing is like the thing matters of how we are taking a natural world raw problem and translating it into a graph ML problem. So for now, do you have any sort of questions, or should I go to the next? That is the topic. Hello.
Yeah, I think we can go to the next part since we covered the introduction right now.
Yeah.
There might be
Is it
questions.
okay?
I think there was one question.
Okay. Uh, will the meeting be recorded? Yes. Can you speak a little bit slowly?
Someone had unmuted, but yeah, we can move forward. No problem.
Okay, I will try to like speak a bit slow. Please let me know like should I like change on my flow or stuff. I'd be happy to. So before like going taking a deeper dive to what GraphML is and all about, we have to learn about some sort of like terminologies here. And very like this. So let's just like forget all of stuff and start with a very simple thing. What's a graph? So coming back here, we all know what actually a graph is. I mean, even we are if we are all college students, I'm assuming here, we can think a graph as some sort of nodes and edges, right? So suppose I am having this some sort of nodes here and the edges. This is a graph, and you can represent. And if we go a bit formal, then you can actually. Is there any questions? Yeah, I guess this session will find in the YouTube. So yeah, so let's just come in here. So suppose we can actually, if we bit formalize the whole thing, then we can actually represent, or we can say that this we can say this is the graph G. This graph G has some sort of nodes V. So V is like this, suppose V1, V2, V3, V4, and some sort of edges E. So suppose this is E1, 2. This is suppose I'm this directed edges. So suppose I have E2, 4. I have E1, 4, and also I have this E4, 3. Something sort of like this. And the thing is, let me just give me 1 second. Yeah, I'm sorry for the interruption. So you can actually think, so the thing is like, so what you're just getting is like, suppose you're having some set of nodes as v1, v2, v3, and v4, some set of edges like e1 2, e1 4, e2 4, e4 3. So this actually belongs to a set. So you can actually say that I have some set of nodes v, and I have some set of nodes e. So you can actually think like my graph G is nothing but the composition of some sort of nodes V and some sort of nodes E. I'm actually trying to formalize the stuff, because when it will be going to some little depth, then there will be using some sort of like different sort of like the symbols and stuff, which might get sometime over the. So I will try to go this thing by little step by step. So here's like the very nice thing of like we can actually present a graph. But let's go a bit advanced now. Suppose you can actually let's just think about a real world scenario. I mean, suppose you have suppose I'm taking the same suppose this molecule like CH3 COOH. So I am having this molecule CH3 COOH. Don't think as this is a chemistry class, but yeah, just some chemistry things alert. Suppose I have this carbon, that is the carbon as atom here. The hydrogen atoms are out there, and they are actually bonded with some sort of bonds. We can actually think this as nodes and edges, as we have like talked previously. But other than that, we all know like carbon has some properties, right? I mean, carbon has their own atomic number, mass numbers, etc., etc. Suppose I'm taking just two things. Like suppose the carbon has some atomic numbers, and carbon has some mass numbers, and number of electrons it has, and etc., etc. So the each and every like atom has some sort of like the properties, and so what we can actually say is like each and every nodes has some sort of properties out there, right? So each and every node, say like hydrogen has also some sort of properties, this carbon has also some sort of properties, and they are actually connected with each others with some sort of edges. Now the thing is like, so so when you just go to a bit more advanced here in the before, like in this before diagram, we do not have any sort of properties of the nodes. In most of the cases, we generally use graphs for actually finding some sort of paths. Like this PFS, DFS are like quite classic thing. But when it comes for the machine learning, then the real world graph has some sort of features. So the features that the node carries is the node features. So suppose, and we can actually represent these features as some sort of like list, like my carbon has some sort of like the features, it has some sort of atomic number, it has some sort of mass number, the number of electrons it has, and some so on. Hydrogen has some sort of like, you can actually jot it down some the important features that you want to have, and you can actually jot it down into some sort of list. But now if I want to formalize the stuff, then we all know like in deep learning or in machine learning, we have some input, and input always has some sort of features, and each feature can be represented as some sort of a vectors. So and in the list, we can actually represent this list as some sort of vectors. So now we can actually think this as like, I have this like carbon atom, and it has some sort of what could I say, some list of like the features, which is the vector here, and it has a bond right there with the hydrogen, which is another node, and hydrogen has some sort of, what I can say, some sort of features. And suppose I'm going a bit more detail here. Suppose I am having this edge here, and this edge is some sort of like some sort of bonds. Suppose it has some bond length or bond angle right there. So this bond also has some sort of features. I guess it's you can understand till here, right? If not, please ask me. No questions?
One question here.
Yes.
So, do all nodes need to have same set of features, or they could, completely different?
Now the so here I can actually answer this thing something like this. You might have this confusion here, like this is a carbon atom and this is also a carbon atom. These two carbon atom will always share the same sort of features, and at the end of the day, they are the same atoms, right? But in general, when you are dealing with it, then hydrogen will obviously have different features. I mean, hydrogen has some different, all over different chemical properties. So if you just don't think in the terms of ml, then it always will have some different properties, and hence it will always have some different features. Does that answer your questions?
Yeah, yeah. I mean, the only intention was to like the two entities that has a relation could have different entity types, right? So they could altogether have different features, right? I mean, a feature that belongs to one node may not be applicable to another node, right? At all. So those kind of things do occur in GraphML. That's the intention of the question.
I mean, suppose, I mean, I cannot understand your question properly,
Yeah. So my
but the thing
question,
is,
in
yeah.
I mean, a naive way, so there are two objects, two nodes in a graph, but the two nodes have some relation, but the type of nodes are not same. So here the carbon and the hydrogen both are like atoms, like something like that.
Mhm.
But what if there is a relation between a carbon and something which is not related to a chemistry, right? So that is something outside chemistry, outside the domain. So they could still have some relation. So they may not have same set of features. Does those kinds of things applicable in GraphML?
Yes, I mean the question you asked can be actually a bit reframed here. I mean, in specifically you can actually have asked in terms of chemistry. I mean, but in chemistry, I don't think so. You can actually relate directly there. But suppose you can actually think of it like, suppose this is me, okay, and suppose this is a person A, and suppose we are friends, right? But suppose I am having another person B, and I am not a friend of B. I am having a different relation with B, right? And this relation B, suppose some sort of a colleague, right? So this actually some sort of answers your questions. Is like these things are actually falling to a same entities. I mean, these two nodes will always have a relation of a friends, but there might be some other nodes which have some other relations.
Um,
So
my
that actually falls under, yeah, go ahead.
I mean, it's slightly different. I mean, I'm not talking about the relation, the different relations. I'm talking about the node types. So here, all the three node types are belong like person, right? All the three nodes are person types. So what if a
No,
node is a
you might have different nodes also altogether. Yes,
yeah,
you can have it. I mean, you can always have it. I mean, if you see a user node interaction graph also, a user item interaction graph, then the thing is that you have some sort of users here, okay, like users, and they are buying some sort of items there. An item is totally different nodes out there. So
correct,
item and user are not at all like alike with each other, but
correct.
they are having some sort of like a relation with each other, right? So this is specifically if you ask about this graph, then this is a bipartite graph
Correct.
where you have these two sort of like a different notions of nodes which are like having some sort of links with each other. So yes, this is definitely possible in this case.
Sure, yeah, sure. Thank
So yeah,
you. Thanks.
how to differentiate between nodes? One can always add a feature like a one hot encoding to the node features. Can you like elaborate on this,
Oh, sorry.
Himanshu?
Sorry, this was not a question, but more of a follow. So like coming back from the previous question, if there are multiple kinds of nodes, like in order to give that prior to the model, one can always add one order encode, like some feature like one order encoding, which can allow the model to learn or like model like different nodes independently. Okay, not independently, but more like in a different way. So like a movie and a user can have, although they are nodes, but they can be modeled differently because they have different one-order encoding. So like I meant
Yes,
to.
I mean, yeah. So the thing is like you're saying like suppose you are having this user node and you are having this item nodes. Both are totally different with each other, and how you're like trying to represent them such that they are related. So in order to show the relations with each other, something like this, like how you're gonna represent it.
Oh,
One way you are saying is like
so
one
like
hot encoding.
features would be just like the features would be some kind of vectors, right?
And yes, obviously,
Yeah.
yes.
So like we can just so like in this vector we can concatenate the one-hot encoding so that the model knows that like this particular like 10 represents a user and 01 represents a
No,
movie.
no, not like that, not like that actually. So in this case, what it actually one of the way that you can actually do is like you can like the similar nodes are like suppose you have this user nodes sets and you are having this item node sets. So you take a different like suppose so one thing I would actually come here is suppose you group the user nodes as one whole matrix, like some set of nodes, like some set of vectors which are stacked with each other will always form a matrix here, and the that is the item nodes will be like combined like stacked with each other for being an item matrix. So all those two will be a whole different entities, and after that you do like for here for this session I do not want to go into a big details because I have to cover the other topics also. But in this case, for answering just your question is like what generally is done like is like the users and the items nodes are actually kept differently, and their relations is actually been like stored on a different sort of like a data structure or a matrix is something like that. So that's that answer. Otherwise, if you want to know more, we can like discuss that on the chat for now.
Okay, makes sense.
Yeah. Awesome. So the thing is, so let's come up with this. So I guess you guys now get this notion of the nodes having some sort of properties, and we're trying to formalize that properties as some sort of vectors. Similarly, like different nodes have different properties. So different nodes have different node feature vector. The term node feature vector is very important here, and you might construct some properties with the edges, which will be the edge feature vector. So now, in with respect to the graph ML, what you're trying to formalize the stuff is I have a graph G which has some X, which is like the node feature vectors, some E, which is the edge feature vectors, and an adjacency matrix A, which shows the topology. So coming up with this a bit more, suppose in the previous case only, I am having this graph, right? So I can represent this as a graph G, and I have this some node vectors, right? This is my node vector for like suppose I'm numbering this. Suppose this is my 1, 2, 3, 4, 5, 6, 7, 8. One has some node vectors, two has some node vectors, and some similarly. So how can actually represent the whole graph on it? We just stack all those nodes with each other. So we keep a reference point like this is my first node, and based on that we try to number the nodes, and suppose I having this matrix here, and in this matrix suppose this is my zeroth index 1, 2, and suppose I'm having this 8th index. The first index will have a vector here which will be correspond to this. Second will have like suppose this is my zeroth vector. I'm just changing the index. Like this is my zeroth node, this is my first node, my second node, my third node, my fourth node, fifth, sixth, and seventh, in order to just correct the indexing properly. So I'm having this like the zeroth. So for suppose we can actually think like the zeroth for the zeroth index, I'm keeping the node feature vector for the zeroth node. For the first, that is the index, I'm keeping the node feature vector for the first node, and similarly this just goes on. And finally, I'm actually getting some dimensional of the matrix, and if you guess it correctly, then I'm having suppose 8 nodes out there, and suppose each of the nodes has some sort of feature. Suppose I'm having 3 features, so there will be like 3 columns, one first column, second column, and third column, and there will be like 8 nodes. So in this case it will be a 8 cross 3 matrix. And generalizing it, suppose I'm having n number of nodes, and each node has suppose f or d number of features, then the that is the node feature vector, that is the x, will belong to a shape of like n cross d, where n is my number of nodes and d is the dimension or the number of, that is the features that the node feature vector is carrying out. So here it actually answers the first question, which is x. So x will always belongs to a feature, that is a matrix of n cross d. Coming another thing is like we can have this edge features. Now this edge features is in general an optional thing. There is no necessity that you always have to put an edge features over it. There is like not at all like a necessity of it, but you might put here. I mean, in this case you have this, you might put that how much the bond length is, the bond angle, how much the bond are making the angle, which might be a very useful information when doing some sort of a task. Like suppose you have been doing a task where you're like classifying each of the molecules as whether they can be suppose they can be adhesive or not adhesive, or suppose these molecules can be helpful to remove HIV or not. Like we can do some sort of classification task, right? So all these informations, these features of the nodes and this edge features are actually very much important in order to compute the classification, right? So in that case, you might include the edge features, but it's not always optional. And in this case, also like suppose the edge features is also like a matrix where it will be have suppose the number of edges. So suppose I having this nx that represents the number of nodes, and ne represents suppose number of edges, and suppose I'm having this f, this letter f, which means the number of feature vectors that the edges carry, and I'm having this adjacency matrix A, which is actually the and this is like a, it's quite self-explanatory. I guess you guys know about what an adjacency matrix is. It's nothing but an n cross n matrix, right? So this is how we can actually formalize the graph, what a graph is in the context of graph machine learning. A graph in the context of graph ML will always contain some sort of code features. It might contain an edge feature, and it always contain the topology, which is the connectivity which can be shown through the adjacency matrix A. So this is how we can actually represent a graph. So I guess you guys are cool with it till now, or any questions? If I see good questions that might take some time, then I will be taking that either to the last, or I will be taking to the chat after the meeting. No questions right now? Great, awesome. So let's come up. So I have actually, so it's actually gives the notion of, I already explained what the node feature is, what edge feature is, what an adjacency matrix is. You guys can have a take a look on it. I have also put some good, I will also try to put up more resources. But for now, I initially have some resources out there. You guys can check out in the speaker notes. So yeah, we completed a big part. Now, this just come up with this concept of embedding. Embedding is like a really cool concept out there. So let me just come up with that. Yeah. So not only in graph, but in NLP also you can have this, or in computer vision also, or in any any like machine learning or deep learning, like an era in the domain, you can actually see that there is always a concept of embedding, right? So you have actually seen, like, suppose I'm having this word king, and suppose I'm having this word of prince, and I'm having this word of queen, and I'm having the word, suppose, mango, or and I'm having another word, suppose apple, and I'm having, suppose, another word, just guess a word, Pikachu, my favorite is actually. So I'm having some sort of words like this, right? Now, our brain can, once we heard about these terms, we know about these terms, our brain can actually differentiate the context of all these words, right? We all know that king, prince, queen all belongs to the royal stuffs. Mango and apple all are some sort of fruits. Pikachu is a Pokemon character, right? But the thing is, like, how you can use this concept and translate that to some sort of like in the machine learning, how you can like separate these things, right? So you need some sort of you need actually some sort of operations that will like take all of these words and then try to like, suppose I'm having this, suppose a three-dimensional space, or suppose in some sort of space, let us assume like in this three dimension, I'm having this, suppose, king, queen, and KQ and prince here. I'm having this mango and apple here, and I'm having this Pikachu here. So what we do is like we translate, like, initially, if you see the general NLP thing, then we all have this some sort of a vocabulary. I'm not going to like go to the NLP much, but we have all this vocabulary initially, and this vocabulary has some sort of like one hot encoding every time, and you use those like one hot encoding to pass under some NLP model, and they provide a new vector, right? So the thing is, like, you give some X to a model, and they provide some sort of a vector Z, right? Which may be of some sort of dimension. Maybe the initial X has some of dimension D, and Z might have some feature vector of like F of dimension F. And this F is that is this vector Z is some sort of a learned representation that has been trained in order to actually capture the context of each of the words, right? So here, after like passing through this stuff, I can actually, we can, if we cluster all this stuff, all of these words as a vectors, then we can actually see that there will be a time when things actually got separated out into different sort of like the clusters, right? So all of these like vectors, the latent representations, the representations as a general term, you can actually think those representations as an embedding. Now, all of this actually embedding only helps us to do all of these tasks of classification, regression, clustering, etc. All of these tasks is actually secondary. Our always primary task will be help to make a model. That model will learn something in such a way that it will that with the each and every input that we are trying to give, it will actually throw out some sort of a feature vector or some sort of a, like a learned representation that will actually try to like have some their own properties, and the entities which will have the similar properties will always group together, and which are not same will be like be go far from each other. So that's what the general concept of an embedding is, or a latent representation is. And in case of graph, you can also like think the same thing, something like how now suppose, how can I make you understand? Suppose you have a network of friends. I mean, suppose this is a friend A having this like friends with B, C, D, E, F, G, H, I, J. Suppose I am having this some sort of a graph, right? So all of this is some a simple graph G. Now suppose I am in a town, and all of these some sort of students, and they actually belong to some different schools. Like this town has suppose two schools. There is a school, suppose I'm having a school L, and another I have a school suppose M. Now suppose there are the students who are friends with each other, but I want to actually group the students who actually belongs to school L, and some of the other students who actually belong to school M. So what I try to do is I take this graph and I push this graph to some sort of a model, and this model, what it tries to do is I mean, there will be a some time when the model actually learns the representation of all the nodes of the graph, and once it learns the representations of all the nodes, then you can actually see something like this, as the similar nodes actually come up with like. Now the thing is that you always have some sort of features, like suppose I am going to one school and my friend is always going to another school. We always share some sort of like common features. At the same times, we always will share some sort of features that will differentiate with each other on the basis of the what school which we are reading actually, right? So there will be a time when the nodes with the similar sort of properties, the schools that they are actually reading will be like getting like far from each other, which are like different from each other, and which will be like similar with each other, will be like will be clustered together in a dense form, but all the connections will not get loosed. So this is how you can actually define the notion of clustering uh, in terms of this, and this is actually been successful only when you actually capture the correct representation of the nodes, and this node representations can only be seen that is when your model has learned some sort of like a generalized representations. So all these node representations, initially you have this some sort of this cluttered graph, and after when you actually clusters the node of the graph, then you can actually see that the nodes in are separated in all of these two classes, right? So in this case, the node has actually initially you put some sort of like every node will have some sort of the input features, right? But after like passing it through the ML model, you will be having this node features, that is the representations, that each of the representations will have some other like the feature vector which will be like differentiating with each others, as I've like mentioned before. And all those node representation, updated node representation that does this as some learned representations are my node embeddings. That's all. So that's actually answers what's the embedding in graphs in node level is. And yeah, so this is how we can actually represent how nodes of the graph can be. Now, initially, mathematically, what we can do is like, suppose I have this, I will not go to the exact operations and the proofs like how the stuffs is actually been worked on. We can actually target it for another session, like how different models learns their own embeddings. But suppose but here's the like the general workflow. You have a graph X, suppose of a feature vector X and like adjacency matrix A, and you put it into a model, and initially suppose this X belongs to suppose R of n cross D, where D is my initial number of input feature vectors, and you put this to a neural network. The neural network that works on the graphs are known as graph neural networks. It's as simple as that. But yeah, it has like the model is like different, it will be always. But suppose I'm putting this thing to a GNN model. This can be any GNN model. Some of the GNN models will be like discussed in the later part of the presentation. But yeah, you have this GNN model and you pass and you actually get some hidden representation Z, which actually belongs to a feature metric of suppose n cross f, where f is my embedding dimension. And once done that, you will be having like this Z vector and this Z will have like this, each of the nodes will have some updated sort of representations. And if you clusters all of these nodes, then you can actually see that similar nodes are like staying together and the different nodes are going apart from each other, are potentially trying to go apart from each other. So this is how the things have been done. And this is actually in the node level thing. Even you can actually get the whole representation of the graphs. What I have actually told you right now is actually in the node level. So if you just think, then the representations which I'm getting is some sort of matrix. I'm given a matrix and I'm also getting an output matrix. But suppose you want to get the representation of the graph. Like in the previous slide, if you go to this, I want to get the representation not only of carbon, oxygen and hydrogen, but I want to get the representation of the whole molecule as a single feature vector. Then how can you do that? So suppose I am having this matrix. Suppose I'm keeping a very simple matrix, right? So suppose this is my first node, zeroth node, first node, and second node, and I'm having this values of nodes. Suppose this is 0, 1, 2. In real world, it's always a continuous value, and it's not in the small dimension. Let us assume this is my like this node representation Z for now. The second node is supposed to 1, 3, and 1, 1, 1 is my third. And this is, you can actually see that this is my updated node representation of for node 0. Next is for node 1, and it's the second like is for node 2. And what I want to get now is actually I want to get the updated representation of the whole graph G, not in the node level, but as a single vector. So what I will get is like, suppose I do some sort of an operation such that I get like, suppose I'm getting suppose a vector of suppose A, B, and C. And this A, B, and C is a feature, is a vector, is a representation that represents my whole graph. Now, I have actually told like, uh, how can I actually say it? Like, you can actually think of this in the image domain also. I mean, suppose you have this image and you pass this thing to a CNN, and then you actually get some sort of a representation before passing it to the softmax. Don't think of softmax. What softmax does is just classifies to, it just gives a probability to the potential, like to the all the classes. The biggest classes actually gets got selected. But before the softmax, you have the you have some sort of representation. That representation actually represents the image, that is my image. Suppose this is my image, right? So similarly, I want, not only I want, so similarly I want to get the representation of the whole graph. And you can actually do by different sort of operations. One operation is like from this axis you either take the mean of all the values, like suppose 2 and 3. So 3 by 3 it will be 1, 3, 4, 5, 6, so it will be 2, 3 it will be 1. Right? So you either take the mean of all the values, or you can take the max of all the values, or you can take the mean of all the values. And like this, you can, so from there you can actually translating this whole matrix to a single feature vector, and it will represent the representation of the whole graph, because you can actually represent a graph as the embedding of the graph as some combined properties of all the nodes. So here the first index is the combined properties of the node 0. The second index of B is the combined property of node 1. The third is the combined properties of node 2. And here you eventually get the whole property of the graph. And after that, you can suppose I have this molecule A, which is suppose some sort of like molecule, something like this. I'm having this, suppose this molecule B, which is suppose and another molecule, something like, suppose a very complex molecule, something like this. And now what you're trying to do is like you want to classify these molecules, whether it can be particularly fight HIV or not. So before that, you translate all this molecule, the that is the big molecule structures, to a very single like like the feature, the vectors, like the representations of ZB and ZA, and after that you put this softmax thing and you get the like, simple classification. So that's how you can actually define the embedding of a whole graph and the embedding of the node. So I guess this actually comes to the end of the second, like the topic of the different terminologies. Now we can actually come to the tasks, different tasks that is been used in graphing. So till now, any of the questions? Uh, if you have some set of nodes having the disjoint features, heterogeneous nodes can also be defined in the same graph. Yes, exactly, exactly. So all of these are. I was actually trying to come up with this notion of heterogeneous graph, but at the same time, I mean, as it's a very introductory session, so I do not want to keep like come up with this all this new jargons of this like complex things. So, but yeah, there exists this heterogeneous graph that I was trying to see means explain before. Yeah, till now, any questions, or should I move to the next part? And I was like properly people like guys, you can properly hear me till now. Hello. Okay, awesome. Okay, so let now here comes the third part of our session today, which is the different sort of task that has been used in graph. So beforehand only, I was actually putting this pressure of like I was taking the embedding into the node level. After that, I came to the perspective that I want to take the properties into the graph level, right? So here actually based on all of this, you are getting some sort of embeddings in the node level. So what you will do with this like embeddings, right? You have to do something. You will do some sort of downstream task, which can be like unsupervised tasks, like some sort of clustering, or you can do some sort of supervised or semi-supervised task, which is actually classification, right? So here comes the we can actually classify the graph ML tasks based on the portion of the graph where the task has been done. So broadly, we can actually classify that into three ways. So the task can be actually be a node level task, it can be an edge level task, or it can be a graph level task. So what a node level task is, you can actually see before here, like in this example of the people, suppose I am having the students here, and now of the which are suppose I'm having suppose in a like imaginary world, I'm having a town where I'm having only two schools. School one is CH1 and school two, and there are some bunch of students out there which are friends with each other, but they do like goes to some different schools. So suppose and all of them are connected based on the are their friends or not, and based on this I want to get an output, like I want to get an output such that I will classify these students based on suppose I represent school one with this color and school two with this color. So what I just want to do is like I want to get some output something like this. Let me just draw pretty fast. So something like this. Just let me keep the edges here. Yes. So so the task is not actually coloring the nodes, but the task is like the task is actually classifying the nodes based on which school they're in. It's actually I'm just keeping the famous example of like Zachary's Karate Club, which is actually a data set where you can actually do this thing. You can do not only in this data set, but you can do in like different sort of data set. But that's one sort of a classic MNIST sort of data set in the graph. So by the way, suppose you are a student, you have suppose you have the location of your school, you have your other friends who actually reads in the school, and you have some other information which is actually representing your school and stuff. So based on these properties or features, each and every nodes has some sort of like feature vector, and you're using some sort of a GNN model, and this GNN model is actually performing is like so suppose initially you have some this node feature matrix of n plus t. This GNN model is actually then like having the z vector, and this z vector is actually the z matrix. I should make it in the capital hands. Yeah. this Z is actually belonging to some sort of a representation of all the hidden representation or the latent representation, that is the embedding of all the nodes, which is actually represented by this Z matrix. And after that, I take this Z matrix and then I use the softmax, simple classic softmax activation function. And this activation function, or in this case, it's just a binary like classification. So you can actually put this into a sigmoid classification. So I expect, or I assume, that you people know this sigma classification, these three software activation functions. So I actually take this and I use this to suppose a simple sigmoid activation, and it classifies to 0 and 1 based on the latent representation it has. So once it has been done on the node level, then we can actually tell that this task is a node level task. So I hope it makes some sort of sense, right? Now coming to the edge level task. So here comes the edge level task. This is like a really cool stuff actually. So suppose very before I've actually we have discussed some sort of an examples, like this is me. Suppose the person A. Person A has this person B as a friend. B has a C friend. B also has a D friend. Now suppose I'm having so what's the probability or what's the chance that and suppose I'm just keeping it a bit more complex. Suppose D also has a friend of E. Now, what's the chance that A and E will have some sort of relation, or what's the probability that A and E will be friends in the future based on the differences and commonalities they share with each other, with their like the immediate friends. So A's immediate friend is B, B's immediate friends are D, E, and C. So there might be a possibility that E might share some common things in common with A, and that might result to be a friend of A. So here's actually the thing. Like you take this problem. So you have figured out that this is a graph ML kind of a problem. So you take this initial graph. So I'm taking this dotted thing out. Suppose you have this initial graph like this, and what you now try to do is like you take to a GNN and you get the latent representation Z, as we have this initially also. And this latent representation will have this n cross f of these dimensions out there. What you're gonna try to do is using this like this representation, you will sort of find the probability in a very interesting manner. It's nothing but suppose my Z would be a matrix, right? Some sort of n cross f matrix. This is my Z, n cross f. And suppose I take the transpose of Z, which will be my f cross n matrix. If I take the dot product of all these, like Z dot products with Z transpose, and suppose I keep an activation function here, then what I will get is an n cross n matrix. And if you see, we already have an initial A as an n cross n matrix, right? Which defines the topology here, but also it defines the connections, right? The connection between A, B, BD, DE, BC can actually be defined using our initial adjacency matrix. But also we can actually define the new connections right there. I mean, using the dot product with Z and Z transpose, we get some sort of like feature, and taking the sigmoid of it. Suppose I am having this 1 to I n, and here also like I'm having this 1 2 I j and n thing. I'm having this like 0 0.9, 0 0.1, 0.2, something like this. There's some sort of like the probabilities. Suppose for the I and jth node, I have some sort of probability, like which is suppose 0 0.9, which wasn't initially. I mean, my A, like the suppose in my A matrix, I'm just taking it for a different color. I'm having the same dimension matrix like as so suppose this is, just consider this matrix as the matrix which we get after the doing the dot products, which is our result out there. And this is suppose the A is our initial matrix, which is I'm taking out in the green. Suppose the I and jth node, so I and jth node has some sort of initial zero, some zero value, but now after taking this to GNN and doing this dot product out there, I get a new value of 0 0.9, which means like I will be having this ith node and jth node, which have a very high capacity or a high chance or a high probability that they will be interlinking with each other Hence, there might be a possibility that they will be friends with each other. So that's how the edge level task works. This thing is actually the classical, like the link prediction sort of task, which has been done in different sort of graphs. And if you think it correctly, then this link prediction is nothing but the recommendation. And in what type of graph you use, if you use in the user item interaction of bipartite graph, then it will be some case that Amazon or any e-commerce site uses. If you use that in the social network, then it will be used like it can be what I don't know about Meta what it uses, but it can be a social networking like website. You can use there. You can also use in like the protein-protein interactions, whether this protein will have a positive impact or a negative impact with some certain of drugs that it's been taken, anything. So that's how the edge level task, specifically the link prediction task works. So, and the third thing which actually come is the graph level task. And I guess I already have told this before. I mean, it's nothing new. It's really simple. And this is, I mean, here's one thing is like, suppose you have a drug. Suppose you have a drug A and you have a drug B. Suppose I have multiple drugs, but initially, like assume that this is a drug A and drug B, and you want to classify whether this whole drug is actually capable of that is fighting cancer or not, right? Fighting HIV or not. So so use this drug. So first, so what is your workflow right now? So if I from the initially what I've told, what I've tried to make you understand, until now, we can actually follow this path that we take this like initial. So what's my problem statement? My problem statement is that I have been given some chemical drugs, like molecular drugs, and I want to classify these like chemical molecular drug objects, like whether they can fight some sort of cancer slash HIV, anything, like some sort of like casualties or not, right? So that's my initial raw like problem statement. I take this, then I initially like take the molecular objects. So yes, if you are like kind of confused like how we can represent this, then there is actually we can actually represent this some sort of an objects as a graph, and a very good job has been done by a Python package called Articate, which is specifically done for the molecular based structures, for in generally in the molecule stuff. We can also like see that there are like different ways where we can actually uh, represent a molecule. We can like represent this thing as like this also, which is a string, which we can use in the NLP task, or we can also use like something as geospatial, not geospatial, sorry, some sort of a three-dimensional structure also, or some sort of a, like a graph type structure also. So we can represent a problem in two different ways. But in case of graph, if suppose I'm having this suppose molecule A and I'm having this thing of B, and once done, I take this thing, I take this molecule A and molecule B to a GNN structure. I get this ZA and ZB for all the nodes. Then I use this like this sort of the function, and this function is actually called a spooling function. So this thing what I've actually done, like we can actually take the mean max of stuff, and we can actually get the single like feature single representational vector from the n cross f matrix. So this operation is actually known as graph pooling, and these are like very simple operations, but you can actually have complex operations also. One is like differential graph pooling, but it's out of the scope there. So you take this and you convert this thing to some sort of latent representation, and after that you put this thing to a softmax kind of function, and you then project this thing to my different like spaces of which classes it will be like in which class it will fall, whether it will fall like it can like prohibit cancer or it cannot prohibit cancer, right? So this is how this stuff works. So this is a graph level task. Before that we have like discussed about the thing of notion of the link prediction of giving recommendation and stuff. And before that, we also came about the classification of nodes and others. Actually, we cannot limit this. I mean, if we say a node level task, that doesn't always mean that we are doing sort of classification. It can be other things also. You can cluster the nodes, which is an unsupervised kind of a graphical problem. You can take the regression of the nodes. So here we are predicting the discrete classes like 0, 1, 2 stuff. In regression, in auto regressions, what you take is like for each of the nodes, you predict some sort of a continuous value based on other like some previous some sort of data. So it's not always, I'm just taking a specific example that node classification is one of the example, but it's not only example for the node level task. Similarly for the edge level task also, and for the graph level task too. I guess for now there is sort of no problem, I guess. Is it everything okay? Then I can move to one of the last parts out there actually. It's not the last. Yeah. Yeah. Cool. Awesome. So we have discussed node level, edge level. You guys can like take a look on this after the meet overs, and my DM is always like open or for asking personally, or you can also ask in the group chat. Now comes a very important thing, which is in transductive versus inductive learning. So here comes. So this is a like a very important stuff. Just you have to watch this thing closely. Suppose I have a graph. I will be doing a simple task of node classification. I'm taking a very simple graph. This is my graph G. Now the thing is, I have this nodes. Suppose I am having this. So the thing is that how the node classification. Before that, you have to understand. Before understanding transductive and inductive learning, you have to understand how the node classification works. I mean, how you define the training and testing nodes. So there are very one of the very conventional way to define this is actually is you take, suppose you have 10 nodes. Out of the 10 nodes, you take suppose 4 to 5 nodes. Suppose you take 4 nodes for training and you take 6 nodes for testing. This is just a very naive example, but yeah, suppose you have these 4 nodes for training, but how you will like make this testing node, how you can actually make this notion of a thing like this all actually belongs to the same graph, right? This all nodes have these connections with each other. So one way to do is you mask out these nodes. What does masking means is instead of having any sort of features, you just zeroed out the nodes. So instead of having some valued features, you just zeroed out the feature matrix, and that's what a naive way of what a masking is. So you suppose in this case, I masked out 4 of my nodes, and 2 of my nodes are used for training. Now in this kind of training scenario, where I have done my training successfully, but during the time of inference, now this thing of this notion of transductive and inductive learning is always comes during the time of inference. During the time of inference, you that unmask all these nodes. Now you use all of these nodes as your like main target nodes. You input all of these nodes, but at the same time, these nodes are actually like having the properties of the nodes which are in the same nodes. So what I'm just trying to say is like, suppose this is my node A and this is my node B, and suppose this is having a node C also. Suppose node B is my node of inference. Now node B, when during the time of inference, node B will always capture some features or some properties of node C and node A and its other neighbors also, which are the same nodes. Same nodes means the node which has already been trained for the training stuff. So it is actually so the thing is like it's not completely a testing. So here you are actually providing the training data indirectly to the like the testing data, something like that. So in this case, during this sort of scenario, when you use during the time of this inference, where your unseen nodes, your masked nodes, uses the properties of the already trained nodes out there, then it's been called as the transductive learning. Whereas in the inductive, so this is the transductive learning. And during the time of inductive learning, during the time of inductive learning, what you actually do is, suppose you have suppose you do all the training to a different graph. Suppose uh, you have this notion of suppose you take a graph G1 where where all the nodes are scene nodes. Suppose this is one graph where all of these nodes are some sort of scene nodes, right? So you can take actually students out there. Suppose in the previous example, what I've actually done is I'm classifying the nodes, or the suppose I'm having some set of students, and I'm classifying the students, where the students can be friends with each other, but also I'm classifying the students on which school they belong to. Similarly, I am suppose I am having 1,000 students, right? And I sample out suppose 100 of students out there, right? So I'm having 900 students remaining. I take 100 students, I create the sampled graph from them, and all of this graph is my training graph now. So I do all my training stuff. I take this graph to the GNN, I make the representation, and all of these things are done. And once done, then I then predict in which kind of like school they belong to, whether they belong to school one or school two, etc. Once done, during the time of inference, now during the time of inference, the nodes which has been taken, so this was my training nodes, these were my training nodes. The other 900 nodes which have been not used is my testing nodes. I take all those 900 nodes, I create a graph out of it where no nodes are actually used for training. So all of these nodes are unseen with each other. No one has any shared properties before. And I will come to this thing of shared properties and sharing the features with each other thing a bit later. But you can see like all of these nodes has been never used before. And in this case, when you do the inference, then this type of doing the inference and training is known as the inductive setting. Now, naturally, you can actually somehow guess it, like the inductive training is kind of what you can say is a bit more generalized. I mean, transductive has some sort of cons. I mean, it already is using the properties of the seen data or the already used training data to give some inference based on the training data. So this is some sort of a con. Whereas in that, but though transductive setting is hugely been like used also in different researches, but now people are always like more focused on coming up with a very inductive setting, where the thing is like there will be, so why people are just trying to come up with an inductive setting is like coming up with an inductive setting, the inductive training setting will actually will depict that your GNN model has learned the representation in a more generalized manner than before. I mean, if the suppose you have been given some unseen nodes out of nowhere, and you have to do some sort of node prediction, or you have to support it, do recommendation like a link prediction task when no nodes have been seen each other. So all of this, so if you can do those tasks well by taking a very small portion of nodes in the training, then that sort of thing can actually be deployed, that yes, this type of model can be deployed, has the potential to be deployed in the real world scenarios also. So there actually comes up this scope of this interactive setting. So I hope you can like understand how the interactive settings actually works. One example is something like this, and this is how the transductive thing works. Like I'm already having some sort of nodes. Now, based on these nodes, this all nodes actually belong to the same graph where I'm like splitting into some training and testing based on the masking. And in the same graph, only during the time of inference, I'm seeing whether this new like testing nodes has some connection with some another node. Whereas in the inductive training, in the inductive link prediction task, you can actually see that I am having a training graph and an inference graph which doesn't relate with each other. And in the training graph, I do the training stuff, I do the optimizations of the GNN model such that it can actually capture the like the node representations well. And I then arbitrarily put that to the like the inference graph, and from the inference graph, I get the like the new predictions, which is much more generalized predictions. So this is how the inductive and transductive setting works. Now we will come to the last part, kind of, which has some really like a significance for this session about the how part, and we will be concluding with some recent GNN models or some important models of our discussion. Though if we try to discuss in one of the model, then it will take, I mean, 1 more hour, I guess, and I don't know how much the time is. Okay, it's been like quite of a time. So any questions, like any small doubts till now, or we can just move to the next part, which is the last part of quiz, kind of, which is the message passing. Any questions? Okay, sure. So now actually comes the how part. Now the how part is something like the question actually always been came about the term of convolution. So we all know what a convolution is. Some of us knows it more on the basis of images, which is the super popular thing. But actually the convolution term has been come up from the signals, and this thing has been then more translated to the different other domains, like not only like sequences but also like the images. But if you think it properly, then the thing is like the convolution, the structures of the data, like image is nothing but a grid of pixels. And here comes a very fundamental question. The data structures in which we apply most of our ML models till now are actually the Euclidean data structures, which means the data structures actually follows the Euclidean properties. And one of the like a very basic like example is the image. Image is how the like the data is a very classic example of like Euclidean data structures. Whereas, but the thing is like the question come, can we actually come up the convolution thing? Can we like expand the meaning of convolution or the significance of convolution over non-Euclidean data like graphs? So that's always been the question, that's always been the motivation, and that's how the different sort of different GNN like models, broadly the two models, the spectral model and the spatial model, and different sort of spectral and spatial model actually came up. And like different like other like very complex model like temporally dependent models are also like very complicated. So, but the fundamental question has always been this: like, can we generalize the meaning or the significance of convolutions over different type of structures of the data, whether it be Euclidean data or it will be a non-Euclidean spatial data? So that has been always the mean. Now, from here, we can actually like derive the convolution from two like parts. One is the spectral convolution, and another is the spatial convolution. But based on the time we have right now, it's already 11:30, and the expected time is still 12. And I wouldn't try to go to the spectral convolution now. And I mean, if you guys like the today's session, then we can have another session discussing all this stuff in more details. But for now, let's just come up with the spatial convolution thing, which is like a much more easier thing to understand and the stuff. So here, instead of convolutions, I will be coming up directly to the intuition of the concept of message passing. I have like previously I've actually mentioned this term where the nodes, one node is capturing the properties of other nodes and stuff, and you guys might have confused like what he's just trying to say, I mean, what the sharing of property means, how a GNN fundamentally works. Now, if you answer this question like in a more detail, it might take a bit more time. But the thing is like for now, if you want to get this thing to be clear in a very intuitive manner, then this is how it's done. So suppose I have, let's just come back to square one, where I have a very small graph, a three-node graph, which is suppose this is my zeroth node. So suppose this is my zeroth node, this is my first node, and this is my second node. Suppose I have this like each node has suppose two feature vectors. Now you guys know what a node feature vector is. So this is suppose 0 1. Suppose this is 1 1. This is suppose 1 0. Now it might not be a one hot vector obviously in every case, but suppose for this example I'm taking a one hot vector. Sorry, but yeah. So the thing is like, so I have this G. I can represent this G in a mathematical form, but I will not do this right now. Now the thing is like, what I will just try to do is I will try to take the node 0. This is my target, like this is my, so the that is my the node of interest for now. And I know that, and also let's just add some another node right there. Suppose I'm having this node 3 also with feature vector of suppose 0, 0. Now I know my initial, like the neighboring nodes are node 1 and node 3. So what I'm just trying to do is I want to take the properties, or I want to share their, I want to make node 1 and 3 share their properties to node 0, such that node 0 can know how much they are similar to one another. I guess this like intuition actually makes sense. So one way I can actually do this is like, first we actually think this thing as some sort of a message. So suppose a message is here is simply like node 3 is actually passing a message, which is here this feature vector, and node 1 is also passing a message to node 0. And what they now try to do is node 3 and node 1's message, that is the neighborhoods message. Here the neighborhood of node 0 is 3 and 1. So neighborhoods of nodes 3 and 1's message gets aggregated, which is 0, 0 plus 1, 1, which becomes 1 and 1. And here, once I aggregate those messages, I update these messages with node 0's message. So this is my suppose message aggregated. I am not actually, now the thing is like, what I'm just trying to say now is far most not at all like related with the actual message passing, how it works. I'm just trying to take it step by step so that you guys can understand it better. So it's just a very nice way of, suppose I'm aggregating the messages, which is the feature vector. And next, what I'm trying to do is like, I am trying to update my message, which is like the updated feature of node 0. So node 0's message, like the feature vector of node 0 will get updated. So we can do this. Suppose we are like doing this with a simple addition only. Let us assume for now. So suppose this is for vector node 0 plus my message aggregated, which is 1 and 1, which becomes 1 and 2. So now in my next, like we cannot say timestamp, but suppose in my next step, what becomes my new graph, or my the graph, the new node becomes, the new node feature actually becomes now is 1, 2. Here it still becomes 1, 1, and here it becomes 0, 0 for node 3, and for node 2 is something like that. And the same thing will actually be done for node 1 also, for node 3 also, and for node 2 also, right? So suppose if I say for now is like, I am having this node 0, I'm having this node 1, and I'm having this node 2, and I'm having this node 3. Now what I'm just trying to do is like, 0 gets its own, no, it's like 0 gets the feature from, suppose I'm taking in colors. Suppose 0 gets the features from 1 and 3. 3 gets the features from 0. 1 also gets the features from, suppose 0 and 2, and 2 gets the feature from, suppose 1. But have you guys have also seen this thing? Once node 0 will get the messages from 1 and 3, and node 1 will get, suppose, updated with it, then node 3 has, like, suppose in one case like node 3 also got updated, like, I mean, this thing doesn't take place sequentially, and you cannot say like node 0's message updation will be first, then node 3, then node 1's. But suppose at my first step, like in my step 1, or in my time step 1, in initial case, suppose my node features, now updated node feature becomes, this becomes 0, 1, and this becomes 1, 1, and 0, 1, it becomes 1, 2, and it becomes like 1, 0, and 1, 1, so it becomes 2, 1. So initially it becomes 2, 1. Now next time if I do the same thing, the same message passing, like the same aggregation, then what I'm just having is like, suppose I am, in order to make it a bit like a more intuitive, suppose I'm coloring this node with red, I'm coloring this node with blue. So this is my like node 3, this is my node 0. I'm coloring this node with green, my node 1, and I'm coloring this node with this black. Now I'm having this thing. Now after the first message pass, like after this step, it was like the initial node. After this step, my node acquires some property from blue also, and some properties from green. Blue has some properties of red, and green has some properties of like green has some properties of red, and this black has some properties of green. I mean, now we can actually know what the properties are. These properties are nothing but the aggregated messages out there. So this is for my first step. In my next step, when I will do the same thing for node 0, 1, 2, and 3, then node 0 is not having only the property of node 0, but it's having the property already the properties of node 1 and node 3. Now next time when it will take the property of node 1, like similarly how I have done in this case, if I do now, then it will not only receive the property of 1, but it will receive the property of 2 also. So like this way, I am not only acquiring the messages from in first time step, I'm getting the messages from my initial neighborhood, something like this. In my second time step, I am actually getting the messages or the information, like each node is getting the information of the other nodes. Maybe it's a neighborhood node or it's a non-neighborhood node. But if you go, it's like for my like in my first time step, in my first message passing, I'm acquiring the initial neighborhoods nodes. That is my first half neighborhood. In the next, I'm getting the second half neighborhood. But if you have like more dense number of nodes, like in my second nodes, in my second pass of message passing, I can acquire a large number of nodes like values or properties in a single pass. So this is how we can naively explain like what this message passing is. But in case of deep learning, I want to have some sort of a learnable parameters, right? So here comes the actual neural message passing. And now the thing is like this is how the message passing is, and this is also how the convolution also works. I mean, what a convolution means. What do you mean by a convolution? You have a picture like this, and you take a target pixel, and you have this like the initial, I mean, suppose you have this pixel out there, you put the kernel. So what you do is like for the next step, the properties or the RGB values of all these pixels get aggregated somehow, and then it becomes the pixel of the feature value of the new, that is for my next feature, that is my for the next filter, that is after my next feature map, that is actually coming from an image of the convoluted, like the image will have the combined features of all those like initial number of pixels. And the same thing is also happening here. So you can see how this like the part of convolution is being like now expanded to the thing of graph. So the concept of the notion of message passing. So this is how a naive way to actually introduce the concept of message passing. Now what we can actually do is, so we can actually say, I mean, initially we can say is like, suppose this is my node v0. So message passing will always have is a two-step thing. The first thing is like I will be taking the aggregated message of my neighboring nodes. So all my neighboring nodes will have some sort of a message. So suppose v0, so my aggregated message will be saying m for node 0. The aggregated message for node 0 will be the average of, or suppose I'm taking some mathematical jargons right there, but no need to worry, it's very simple. Just writing this for now, and it will be uh, just 0 dj. What this means, I mean, I have written this equation of what this equation means. This is a neighborhood function. What a neighborhood function means? The neighborhood of node 0 will provide me the set of v1 and v3. The neighborhood of node 1 will provide me a set of v0 and v2. So now you know what a neighborhood function is. So neighborhood function will be providing or returning a set of all the values of the all the node values of the which is the neighborhood of my node of interest. So I am iterating. Suppose you are iterating for all those neighborhood nodes. You take all those neighborhood nodes and you sum up all those like the properties, that is node feature vectors of those neighborhood nodes, and you then take the mean or the average by the number of like neighborhood nodes you are having, and you create the updated message out. So that's your aggregated message. After that, that's my step one. My step two will be the updation step. And in my updation step, if you can see in the slide, what it's now taking is like it's not just taking the average. Here it's just taking the average of suppose it's my H0 now. H0 will now become the average of initial node 0 and just one. Yeah, the initial node 0 and the message which has been echoed for node 0. So that becomes my updated. This is how the message passing works. Now coming to the level 2 of message passing, means for now, if you see, then these are just some discrete functions which we are applying. We are just doing some sort of, if you see, there is no learnable parameters, right? And how you can actually keep this notion of deep learning? How you can like apply the notion of deep learning to this simple sort of like functions of aggregations and applications? So here comes the general message passing. So that's the mathematical representation of message passing. I'm just like using this here because it might take some time. I knew that it might take a time to come through this slide. So come to this slide. So I already created it. So suppose you have this. So as I've like shown in the initial slide before, you have this aggregated message. So you have this aggregate. So suppose for now suppose you have a initial graph. You have a graph of node. You have an initial graph with x and a, and this x and a has like x is a feature matrix of n cross d. But suppose I'm having this sets of v, which is the node sets, the set of nodes which are actually there. Suppose there are v0 v1 until vn. Suppose I'm taking and suppose my node of interest is vi. So for that node of interest vi, I'm collecting the message for all those nodes mi. So I'm collecting all the aggregated messages. So that will be my aggregated messages here, and that will be suppose some sort of aggregation function. Let us assume that the aggregation function is g, or you can take any function f. Let us assume that's an any function. And what you do is like you do the aggregation. Initially, I was just doing the aggregation, that is the summation or average. But now you just take a new term, which is the weighted aggregation. That's it. It's that simple. It's just like initially what I was doing is like I was just taking nothing but the discrete values of v1, v2, and like the aggregate, that is the neighborhood nodes values. But now instead of doing that, what I'm just trying to do is just put a weight to all those values and then activate it. So what it now becomes is some of sort of a function of my weight parameter w, and you can know that for each and every node, like x0 is a vector, right? It's a r cross d vector. And suppose I want to project it to a new feature vector which will have embedding dimension of suppose f. So my w will always be a feature matrix of a parameter of d cross f in like dimensions. So this will be my w, and this will be a function of my learnable parameter, the weight w, with my, that is for all xj's that actually belongs. So we can actually write something like this, like an xj for all j, that is for all node j which belongs to the neighborhood of I. I think you guys can take some clarity from here. And actually, so message aggregation is some sort of a function, an arbitrary function, any kind of function it can be. I mean, I can show you what sort of functions it are, some of the functions which has been used, but the functions which takes a learnable parameter that learns how much weight to assign to each of the like the node feature values, such that you might learn something in order to finally like differentiate between one nodes to another nodes, right? So you get the messages. So you take the w, and you take all the neighboring nodes, and you then aggregate it. And one way typically to do this is something like this. All I've done is like I've added this WJ here, nothing else. It should not be J actually, it should be W only. I mean, because the for any layer it will be a fixed thing, and some of the aggregation function are like sum is an aggregation function, that is you what you do is that you do the weighted sum. You either take the mean or max, you take the average, or it can be a very complex function. I mean, it can be an NSTM also, it can be a GRU also, so it can be a very simple thing like sum, mean, max, or stuff, or it can be a very complex aggregation function too. Updation, how you do the updation. Now, updation is also some sort of a same kind of function. Instead of just adding the message with my initial nodes like B, so if you see in the previous slide, this is my updation where I'm just doing the average of V0 and M0. But it's not only that, or what you do is just you just do the V0 plus M0, and it's just it. But instead of doing this, what you do is now you take the weighted sum. So so the thing is like you take another parameter. So let's just tell it theta, because W and theta are different parameters out there. So one parameter is actually involved in learning the aggregation. How should I aggregate the messages? I will learn some values, or I will learn some representation such that I will be aggregating the node features correctly to distinguish them. And the updation, that is the updation parameter theta, will take care of how should I update the aggregated messages such that I get the correct updation of the final node values. So let it be another learnable parameter, which is theta. And once it's done that, we take in another function, and here the function f and g are nothing but some sort of an activation function, and you always need an activation function. Otherwise, you do not project into non-linearity. I mean, otherwise you always keep it in a linear function, but introducing an activation function will be linear. So the thing is that here f and g are some sort of like activation function. Theta is a learnable parameter, and m is my aggregated, like the aggregated message for node I. And this thing will actually happen for all sort of nodes in the same time. So now you might wonder, I mean, before that, what we can do is like we can actually what we can actually do is like we can take so we have this notion of like we took the step one of aggregation, we took the next step of updation, we combine this thing, then we have this thing of step of the neural message passing, which is this part is the updation part, and this part is the aggregation part. Now you can actually see how a node gets updated. So so the black box GNN is what the black box GNN is doing. This is actually doing this thing. It's taking some messages from the neighboring nodes for the node of interest. It's combining the messages with using some learnable parameters. It's updating the messages at the same time and assigning to that same node every time. And that's actually happening for one layer. So if you just come up here, then if you see one GNN block, then one GNN block is doing this. Suppose this is my layer 1, and in this layer 1, I'm having this thing. Similarly, in layer 2, suppose I'm having another GNN in layer 2, I will be doing the same thing. But now, not only I'm capturing the context of my initial neighborhood, but maybe I can capture the context of the whole graph right now. As I have like saw, I have like you saw in this slide. So that's how the thing works. Another like a concept, if you have actually seen the Entune's like video, I mean that's my way how I actually started deep learning. So there is like the concept of vectorization, right? We cannot like always iterate for all the nodes, and I mean it's just really unoptimized, so you have to like vectorize it. So coming back, last time, I mean just bear with me, it's just the last time I'm taking the coming back to square one. I am having this g of x which belongs to r of n cross d. I am having this a that belongs to n cross n, and I'm not taking any sort of edge features. I do not want to complicate stuff now. So the thing is like, and I put this thing to a GNN, and which is my first layer GNN, and what it does Suppose it does initially matrix multiplication with the node feature matrix. So one way of like doing this is like you have a node feature matrix W, you take the X, so you have like, so suppose my W is actually belongs to suppose D cross F. So you take this, you take the W and X, and after that what you do is you multiply the W and X with your like the what I would say is your that is the adjacency matrix A. But just one thing to keep in mind: the A which here we do is not only the string 1010, but rather than this, what we do is that we normalize the adjacency matrix in order to avoid the numerical computation. So once this is done, if you see it like properly, though this is a very naive sort of vectorization of GNN, as we do not have much time now, so I'm just doing something like this. So this is how I'm trying to vectorize the whole process right here. So what it will do is, like, suppose after doing the W into X, what you're getting like, so if you have this graph now, so what you're trying to do is like you are trying to, suppose this is my node 1, node 2, node 3, node 4, and node 5. So you're trying to project this each of the node feature vectors to some of the another like to, so independently you're projecting each of the node feature vector to some another dimension. So suppose it was my initially a d-dimensional feature vector, you translated that to an that is projected that to an f dimensional vector, right? So now it becomes, suppose an intermediate, I'm saying an intermediate that belongs to R of suppose n cross F. But how you can do this notion of aggregation? How you will aggregate the stuff? Suppose I'm having this 1 0 1 0 0 1 1 0 1 0, and you have this W and X. So what it will do is like for each of the node, now suppose I'm having this node 1, node 2, and like node 3 connected with each other. So what it will now try to do is it will try to so what I will get is like I will get the node 1's feature. I will, so what it will get is like, suppose this is my node 1, this is my node 2 and node 3. So this will be 1 into node 1's feature plus 0 into node 2's feature plus 1 into node 3's feature. And this will how it will create the aggregation. And this is how you actually define the aggregation into a vectorized format. Now, one thing for sure, you cannot complete the thing of the neural message passing thing or the convolution thing in just one row or in just like a subpart of one slide, and it is actually a topic of another session. But how, for now, I'm just concluding here like how this message passing or this notion of message passing works. And based on this message passing, this is how you're doing this message passing. Now you can actually use different ways of message passing. I mean, this is a very nice way using like taking out different variations. I mean, one is like doing like this. Now if you add an attention mechanism to it, then it will be a whole different GNN. If you add some other like different sort of mechanism, then it will be some other sort of GNNs. If you add some sequential thing like LSTM and GRUs, then it will be a gated kind of a GNN. So based on that, based on how you are applying your message passing function, there there are like several popular GNNs. Some of the popular GNNs are graph attention networks. Another is the graph convolution networks. You can actually see the nodes here, and the archive links are also there. So the graph attention network, C is the graph sage, the E is the gated graph at and the attention function, the D is the gated graph networks, which is actually using GRU and the sequential thing, and E is the very recent graph transformers. So coming back to next, you also have very complex graphs model like the very recent graph network which has been actually used by Twitter AI research, which is the temporal graph networks. So it's actually been so in one word what we can actually say is like it actually is used to define, it's a general, so Twitter has actually come up with a very generalized and a robust model where they can actually do the graph kind of predictions of the graph level or node level or any sort of graph task for the temporal graphs. So I guess temporal graph is a thing that we can actually discuss on some other day. In one word, you can actually think that the graph, you can actually think the molecular graph as a temporal graph. Why I'm saying this, like suppose in t equal to 0 second, suppose I am having this structure right here, which is my H2O, like my water thing, and which are, or any kind of like the bonds of molecule. And suppose for t is equals to 0, they have some XYZ coordinates and some sort of like acceleration. But in t is equals to 1, the acceleration changes, the x and y z coordinates changes. So the graphs in which the node feature vector changes, the topology also might change, the structure of the graph, that is the structure of the graph might change, the node feature vector, edge feature vectors might change through time. Those are known as the temporal graphs. Now there are like different variations of temporal graphs which are thing of different like session. So yes, here from here also some of the issues that actually comes in graphs is about the scalability. I mean, yeah, this is actually worth mentioning. Bear with me for more like 5 minutes. Like as we have like actually shown you, like a graph can be hugely sparse. I mean, we actually define the topology of a graph or how the graph is structured is through by the adjacency matrix. But think of the graph that or the network that Facebook uses or any sort of very commercial firm that actually uses. They uses a graph which is having millions and millions of nodes, right? And if you just see, if I'm taking the very simple graph like this, then then you can see the number of zeros. There will be more number of zeros than more number of graphs and more number of ones, right? So this thing, this phenomenon is actually termed that this is very sparse in nature, this type of graphs. So the graphs are generally very much sparse in nature. That's why scalability is a very very common issue. But also keep in mind one thing, that in like when you will be applying GNN models, then we do not take adjacency metrics directly. If you apply the stuff in PyTorch, then actually you can see they actually use a stuff known as the coordinate format, or in short COOP. So what they do is like, suppose I'm having a graph of 0, I am having this thing, suppose 0, 1 and 2. So instead of suppose I am actually taking a matrix of 0, 1, 2, and like 0 has nothing, 0 has connection with 1, 0 has connection with 2, 1 has connection with 0, nothing, and 0 and 0, 0, and yeah, something like this. Instead of doing this, what they try to do, so this is my adjacency matrix, which is kind of sparse. What they do is they actually allocate this to actually to cross the number of the edges that actually forms. So it will be like 0 is connected to 1, 1 is and 0 is connected to 2, and suppose 1 is connected to 0, something like this. So here it becomes what it becomes. It becomes a 2 row, and so 2 cross 3 kind of graphs. The two cross 3 sort of a matrix. So this is actually two format, and if you see, then the number of elements here will be hugely small than the number of elements that you can see in the adjacency matrix. And here it actually deals with the sparsity, but still, in terms of like scalability, graph machine learning has a lot of issues. I mean, unlike transformers, which is, I mean, transformers is actually a type of an architecture which is like really not only useful in terms of predictions, but is like very much friendly and very much useful in terms of hardware usages, because it provides a hell lot of like a scope of parallelization where other like that is the architecture doesn't. So that's one concern. Other thing is the same thing is the computation constraints, the generalization of the embeddings, what I've actually said, transductive versus inductive learning, and why not use transformers, and why only we are like, why we are like coming up with this new domain, and why not we use transformers for the graph sort of problem, because there have been papers which are like now currently trying to use this issue that what we can only use transformers, and only we might not use graph for some sort of task. So there are some issues there. So yeah, that concludes the initial introductory session, and I'm sort of in time. And I'm sorry if I sort of like rushed in some ways, but yeah, pardon, I mean, we cannot stretch a session for more than 2 hours. I mean, it can be overwhelming to grasp each and everything in one take. And also, like I'm kind of like always open in the chats. You can like contact me, or you can also write in the chats to about any sort of like issues or any confusions that you're facing. Yeah. So need to drop. Yeah. Thank you very much. Thank you.